Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Safuan Mustamil, and I will replace Dr. Zaman for this thermodynamic class. So, from before I start my teaching, I will, for Muslim, should we start our class with the Al-Muqta' Al-Fatihah, and for the non-Muslim, with your own way. Okay, as we know that heat is transferred from the hot to cold object. It's never from the cold object to the hot object. Okay, in the first law has said that heat, the energy can be changed from one form to another form, but it cannot be created or be destroyed. The example is I have a warm soda can, and I put into the bucket of ice. Then the heat from the warm soda can will go out to the ice, not from the ice go to the warm soda can. That's where the heat will transform. So it's never from the cold to hot. It will be a hot to cold object. Okay, second law of thermodynamics. In order have first law said that in order to change energy from one form to another form, it will produce two kind of useful form, which is a more useful form and less useful form. And heat is the less useful form. Okay, this the formula. W in are equal to W out plus heat. Example, W in is my fuel, and this W my generator. My generator will produce a work and always also produce a heat. Then the heat is a waste. I can't use the heat. So the W in will always be greater than W out. Okay, the objective we learn of second law of thermodynamics. First is to establish the direction of the processes. Then to provide the means of the quality of energy, which is relate to how much of work we can get from the energy. Then another objective, the establish the theoretical limit in the performance of the direction. And another last of the objective is the establish the condition of equilibrium. Now I will erase first the whiteboard. I will explain about the thermal reservoir after this. Okay, the definition of thermal reservoir is a thermodynamic system with a heat capacity that is large enough that when it is in a thermal contact with another system of interest or its environment, the temperature remains effectively constant. Okay, in easy word, that if we release heat into the reservoir, the heat will not noticeable according to the temperature of the reservoir. Okay, the example of reservoir is such as ocean, lake, atmosphere. I can give an example that if a factory that built beside of the ocean, then when the factory want to release the heat, it will release the heat through the ocean. Then the heat will lost at the ocean because the capacity of ocean is very big. So it's noticeable for the marine to feel hot. Another example is like a UMP pekan lake. If we release heat on the lake, the temperature of the lake will not increase because this thermal reservoir, the pressure of reservoir does not change irrespectively of whether heat is added or extract. Okay, reservoir can be two which is it will heat source and heat sink. In a heat source, the reservoir will supply the heat to the device. Okay, such as like this. This a boiler. The reservoir will supply heat to the boiler. Okay, the example of the reservoir that we can apply on this heat source is a furnace. Okay, in the heat sink, the reservoir will absorb the heat, such as like this. This is a condenser. The heat will send out to the reservoir. The example of the reservoir that will absorb heat, such as like I said, that ocean, lake, and atmosphere. Now, after this I will explain about the two statements that second law that people state of the second law of thermodynamics. Okay, now I will explain the two statements that I have said just now. That statement that people use for second law of thermodynamics, which is Clausius and Kelvin Planck. Clausius statement and Kelvin Planck. Okay, we will go to the Kelvin Planck first. Okay, in the Kelvin Planck statement have been stated by Lord Kelvin. Okay, he has stated that it is impossible to extract energy by heat from a high temperature energy source and then convert all of the energy into work. At least some of the energy must be passed on to the heat of a low temperature sink. Okay, this can show with a heat engine. In heat engine, they have a high temperature reservoir work, mechanical work, and low temperature reservoir. Okay, from the statement by Kelvin Planck, he said that the heat will absorb from this high temperature reservoir will go to the will transfer to the mechanical work. some of the heat will transform to the mechanical work, and the remaining parts of heat will reject to the lower temperature of reservoir. Then it will, after that, it will be back to the original state. Okay, we can find the efficient of heat engine. Calvin Payne said that the efficiency of this heat not 100% will go to the work, because some of the heat will transfer to the lower reservoir. Okay, this how to count the efficiency. To find the efficiency, Q1 minus Q2 over Q1. Then the efficiency will equal to the 1 minus Q2 over Q1. Are you clear? If you're not clear, I will explain about the steam power plant, the another of example of a heat engine. In the power plant, there is a boiler. Then there is a turbine. The power plant also has a condenser to transfer out the heat, and there is a pump. To make the heat back to the original state. Okay, first of all, at the boiler, the heat will be absorbed. The reservoir will produce heat for the boiler, such as a furnace, like I talked before. Okay, it will give a heat to the boiler, then it will transfer to the turbine to produce a work. Mechanical work. Then the remaining heat at that will transfer to the condenser, which is a low temp. The condenser will transfer out the heat to the low temperature reservoir. After that, the low temperature will go to the pump will back to the boiler. Then it will absorb heat back from the reservoir. This cycle will be do again and again and again. Right. After this, the next statement is I will explain about the Clausius statement. For that, I will to erase this whiteboard. Clausius statement. And now is the Clausius statement. Clausius statement has been stated by the Rudolf Clausius. It's not mistaken. Rudolf Clausius is an engineer at German. Okay, in his state, he stated that heat cannot spontaneously transfer from cold region to hot region without an external work being performed on the system. Okay, the example of this example that have been given by the Clausius is in a refrigerator. Heat flows from cold to hot, but must have the external agent, which is the refrigerant system, because for on the statement of a Clausius, it's not a logic for hot from cold to hot without external work. Okay, I will give the example in a refrigerator. I will draw first the refrigerator. Okay, these are the expansion valve. I will explain it later. These are the evaporator. This is the compressor. Then these are the condenser. Okay. Expansion valve. At this area, where this there's a compressor. This is the evaporator. This is the condenser. At this point, there is a warm liquid refrigerator. The warm liquid refrigerator will through the expand valve and will be expand in the low pressure liquid right here, and the liquid will go to the after the liquid be low pressure. The liquid will go through the and go to the evaporator coil. At the evaporator, there is a fan. There is a fan that will help to boil the coil, which is to absorb heat to the coil. So at here, first it is liquid, right? Then it will go through the evaporator, and the evaporator will heat. There is a heat will transfer in to make sure all the liquid been the gas. After it has been the gas, the function of the evaporator is to evaporate water to the gas. And here it will be totally gas. And the temperature will become low. And here, the gas is too cold to be touched. After that, it will meet the compressor, and the compressor has a pump. The pump will sink the gas to the compressor. Usually they will use such as a piston type of the compressor. At the compressor, the compressor will compress the gas to the high pressure. Then after it go out, it will be the high pressure gas. After that, it will meet the coil, which is the condenser coil. This is totally gas. On the condenser, that also like the evaporator, there is a fan. This fan is help to help expand the space of area of the coil to absorb the pressure. Then there will be a blow. There is air blow to give the heat out from the condenser. Then the gas will through the condenser and will be condensed to be a water. That will be a totally liquid. Then it will go to the expansion valve. At the expansion valve, it will go through the process over again and again. Okay, that is for the Celsius statement and the refrigerator. I will next will be the reversible and irreversible. Oh, it's raining, right? I hope you don't sleep in my class. Okay, now we will move to the reversible process. Reversible and irreversible process. Okay, what is the reversible and reversible process? reversible and irreversible. Okay, the root of this process is reverse. Okay, for the reversible, it's a process that can be reversed. Reverse without affecting environment, without affect environment, such as our pendulum. Okay, this the reversible process. There's this piston. It can be moved in and move out. That's a reversible process. While the irreversible process is such a short definition, which is a process that cannot be reversed. Okay. In this world, all the process are irreversible process. This occur because of the friction. Friction will transfer heat into the environment, so it will cause the environment to increase the temperature. And another causes of the irreversible is the heat transfer, such as we cannot reverse a process without a heat pump. If we use a heat pump, the electricity will change to the heat and it will costly. Okay, after this, we will go to the next, the last subtopic, which is the Carnot cycle. Okay. What is a Carnot cycle? Okay, Carnot cycle is being proposed by an engineer. His name is Sadi Carnot. Okay, so Carnot cycle is a cycle that working on a reversible process. As like before I show you the reverse, it can reverse the process. Okay, now I will explain about the Carnot cycle. Imagine I have a piston. Oh, there's a heavy rain. I hope you can hear my voice. Okay, this piston, there's a gas, and I put rock on that to give a pressure for the gas. Then I take this system and I put to the on the reservoir. Which is a hot reservoir. I put a hot reservoir is to keep the temperature up. So heat will transfer to the gas, the QH. After that, we will remove the rocks, a few rocks from the system to this. Then it will produce like this. The gas will expand a little high than before. This is the isothermal process. Okay, we will draw a chart here. Diagram, PV diagram. Okay, first of all, I put this as A, then as a B. The system will start at a certain pressure and a certain value here. Then I put to maintain the temperature, I put a hot reservoir. That will be the isothermal process. So if isothermal process, the line will be like this, quite light to the brown. Yeah. And here this T1. The heat is absorbed into the system. Then I will continue the process with the adiabatic process. I will remain in the adiabatic process. There is no heat exchange, right? Then the temperature will decrease from this T1. Temperature will decrease to T2. And we will remove more rocks, and I left it as one rock here. Then the gas will be more higher than 4. So this is T2 when these are adiabatic. No heat exchange. So the temperature will decrease. Then to get a Carnot cycle, okay, this is C. I use a pen to this is C stage. The B stage go to C stage with the adiabatic. So to remove C is at the isothermal line. So the C stage will be here because then we will put isothermal process to maintain the T. So we put the system, this system to put at the coke reservoir to keep down the temperature down to maintain the T2. Then we put we put more marbles, more rocks, so that isothermal process. Okay. Then to get, then we go to the then we will get the D stage. From this we got the D stage. D stage. Along from C to D, we use isothermal process. Here the heat from the system which have been transferred from here is a high heat. So the heat is high here will transfer to the cold reservoir QL. So D will be at here. Then QL will be transferred out from there, from the system. Then from D, how do you want to go to get to the A? We will put more marbles, more rocks to get to the A. It will we use a adiabatic process like B to C stage. We maintain we no heat exchange at this process. Okay. This one is called the Carnot cycle. This diagram will show the Carnot cycle. This is a Carnot cycle, and this is a Carnot engine. With the piston have shown it can be like a Carnot engine where the piston are moved upwards, downwards, and then upwards back. Then it will be back to the original state. And then I think this end of our lesson for today. If you cannot more understand from me, you can ask Dr. Zaman after he back from the Korea. Then he will teach you more than that, better than me. I hope that will be enough for today. We end this class with a tasbih ifrah and surah Wal-As. Thank you for your attention. Assalamualaikum.